Last time we studied chapter number 12, and in chapter number 12 we studied about radiation, its properties and things like that, and there was nothing much heat transfer related to it actually. Now we are going to go towards heat transfer issues related to radiation heat transfer. This is chapter number 13, radiation exchange between surfaces. So we are not going to go into a lot of depth in this chapter, but we are going to cover only specific number of topics. So inshallah today we are going to finish chapter number 13. It's one lecture is enough for it. And next class chapter 14, and that's it. So in this chapter, the most important thing is the view factor. So we are going to study the view factor and then the black body radiation exchange. Okay. So what is a view factor? View factor is basically it's by the name view. Okay. So a body is emitting radiations. Radiations are coming in all directions. Now where are these radiation going? It depends upon the view of the body to the other bodies. If this body has a larger view for another body, then larger number of radiations will go to this other body. Okay, if the other body is far away, then it's a small view of that body, and there is other bodies as well, because radiations are emitting in all directions equally. Okay, so it's really about that. So if I make two bodies very close to each other, then the view factor becomes 1, because this is in the view of this body is totally on this body, and there is no other body over which it can view. So it's about that by the name view factor. Well, let's study. Consider the problem of radiation exchange between two or more surfaces. This exchange depends strongly on the surface geometries and orientation. So we have bodies which are exchanging radiation, and this exchange of radiation is hugely dependent upon the geometry of the body, what kind of body is it, okay, and their orientation. Okay, so if this is my body, and suppose the radiations emitted from this surface are in this direction, so none of the radiation will be transferred from this surface to anything which is behind the body, because radiation move in the straight directions. Okay, they do not get curved, they move in the straight directions, in the straight path, and it's a hemispherical position. So the view of anything behind it is not there for this surface. So it's, however, if I change the orientation, now it's a complete view here, and there is no view at the back here. So how much is the amount of radiation transferred from a surface to the other bodies actually depends upon the geometry of the body, what is the shape of the body, as well as its orientation. So if I change the orientation, the amount of radiation will change, which will be transferred from this body to the other bodies. Okay. As well as on their radiative properties and temperatures. Obviously, it depends upon the temperature and their radiative property. Radiative properties are emissivity, absorptivity, things like that. Assume that the surfaces are separated by non-participating medium, a medium such as vacuum that neither emits, absorbs, or scatters, or has no effect on the transfer of radiation between surfaces. Now, in our analysis, when we consider the radiation exchange between bodies, we assume that in between there is vacuum. Actually, there is not vacuum, air is there, but air poses very minimum amount of resistance to that radiation transfer. Okay. So we assume that it's not posing any resistance. And resistance could be in the form that there are radiations emitted from this surface, but for reaching over to the other surface, if it is absorbed somewhere in between, then that means this body is or the in-between medium is posing a resistance, because it's not allowing all of it to be transferred. It is absorbing some amount. Or if the inside medium emits radiation, then the radiations will be increased. Okay, so that's producing a disturbance in the radiation transfer. So what we assume is that the medium in which radiation heat transfer is occurring, it's non-participating. It does not do anything to the radiation, neither absorb it, neither emit radiations, nor scatter it, nor change the direction. It's not like that. A vacuum meets these requirements exactly, and most gases meet them to an excellent approximation. So if we have vacuum here, you know what is vacuum, right?
No air.
No air, nothing. Okay, if we have vacuum here, so obviously vacuum will not pose any resistance to the radiation heat transfer. However, most of the gases or the air in which we live in, they also behave as vacuum to a certain level of approximation. Okay. Well, anyways, enclosures. Enclosures consist of two or more surfaces that envelop a region of space, typically gas-filled, and between which there is radiation transfer. Enclosure is any enclosed surface, any surface which is closed. Okay, and there are radiation transfer going within those surfaces. However, they do not leave the enclosure. They remain within the enclosure. Okay. Virtual as well as real surfaces may be introduced to form an enclosure. Sometimes we have real surfaces. Sometimes we can imagine a virtual surface, which is not real. We imagine that if there is a surface here. Okay. You'll see a problem in which we will imagine surface as well. A non-participating medium, obviously the medium has to be non-participating. It should not pose any disturbance in the radiation heat transfer between surfaces. Each surface of the enclosure is assumed to be isothermal, opaque, diffuse, and gray. So all the surfaces of the enclosure are assumed to be isothermal. So that means there is no temperature variation within the surface. It's opaque, so it does not transmit any radiation. It is diffuse, so amount of radiations emitted by any of the surface of the enclosure. Suppose this room is an enclosure. So amount of radiation emitted by any surface of this enclosure is diffuse. It is moving in all directions. And gray. Gray means independent of wavelength. Okay, so this surface is not just emitting a specific wavelength. It's emitting all the wavelengths. And similarly, all the surfaces are emitting all the wavelengths. And to be characterized by uniform radiosity and irradiation. So there is a uniform level of radiosity and uniform. That's a Kirchhoff's law. For an object to be isothermal, it had the amount of incoming radiation should be equal to the amount of outgoing radiation. Amount of incoming radiation is irradiation, and amount of outgoing radiation is radiosity. Okay. The definitions here are important, right? So just make sure we can ask anything out of these definitions. What does diffuse mean? What does gray mean? What does opaque mean? What does isothermal mean? What does radiosity means? What does irradiation means? We studied that in the last chapter. Okay, now let's come over to the view factor. Basically, radiosity. Radiosity is what? The amount of radiations emitted by the surface. Total outgoing radiation from a surface. Okay, and we represent radiosity as J. We discussed that in the last class. We represent radiosity as J. Okay, so and J has unit in watt per meter square. It's the amount of radiations emitted per meter square, right? So what will be the total amount of heat transfer from the surface? What will be the total amount of energy emitted from the surface? Okay, so it will be J is watt per meter square. You have to multiply this by A. Okay, so if I multiply this by A, the area of the surface, then yeah, so then it will be, this is in meter square, so that's the amount of radiations emitted. So this is basically what? Q. Q is equals to AJ. It's clear? Yes. Now, for most of the times, we are not just interested, we are not just interested in what is the radiations emitted by the surface. We are interested in how much is the radiation exchange which is happening. So we are concerned with two bodies and the radiation exchange between two bodies, because we are concerned with how much is the heat transfer from one body to the other body, right? For how much is the heat transfer from one body to the other body, that means how much is the radiation exchange from one body to the other body. So it's not just how much is the radiation emitted by this body, it's how much is the radiation emitted by this body which reached the other body. This is the point of interest for us. Okay? How much is emitted by one body which actually reaches the other body? Because radiations are emitted in all directions. Maybe it is emitting a lot of radiation but it does not reach the other body. Then the heat does not exchange from one body to the other body. It is exchanged with some other bodies.
With the medium?
No, medium is non-participating. Medium does not participate in anything. Okay? So it's like the cameraman. It does not participate in the lecture. Okay?
But he is there.
But it is there. Medium is there, obviously. Is it clear? So the thing is that now the point of view factor comes into account. Because this is the amount of energy emitted by a surface, but it does not mean that all of it reaches the other surface. So we have to introduce a factor F. That's a view factor. It's kind of a percentage. Is all of this emitted radiation reaches the other surface? So I have one surface A, other surface B. The amount of energy radiated from A, what percentage of it reaches to B? So that's the view factor. If 100% of A energy from A reaches to B, then it's 100%. Then F will be 1. If none of the energy reaches from A to B, then it's 0. So view factor is basically a percentage. How much energy is emitted by one surface reaches the other surface. Okay? And its value ranges between 0 to 1. Okay? Anyways, so view factor, what will be the formula for view factor? View factor will be Q upon AJ. Okay? View factor will be Q upon AJ. And Q is, so now we say is that, let's say two bodies, two surfaces, one surface is I, other surface is J. So amount of energy emitting from I which reaches J. So since it is emitting from I, so the surface area of I is important. Okay? And the amount of radiosity emitted by I is important. That's why it's AIJI. Okay? That reaches J. So here the view factor Fi to J is important. Okay? So Fi to J is equals to Q. That means when I write I to J, it means amount of energy emitted by I which reaches J. If I write J to I, that means amount of energy emitted by J which reaches I. Is clear? So you understand this formula now here. So consider these two surfaces. Suppose this surface is I, this surface is I, and this surface is J. Now, how much is the amount of energy radiated or emitted from I that reaches J. Now you have to understand one thing, as we discussed earlier, that all the bodies are continuously emitting radiation and absorbing radiation both at the same time, right? All the bodies are continuously emitting radiation and absorbing radiation at the same time. So if there are two bodies, if I want to know how much is the heat transfer, net heat transfer between the two bodies, then I have to determine how much is the heat transfer emitted from this, from one body and is absorbed by the other body, minus how much is the energy emitted from the other body and absorbed by this body. Okay? So the heat transfer is occurring in both ways, but the net heat transfer will depend upon if in one way heat transfer is large and the other way heat transfer is less. So the net heat transfer will be in the larger direction. Is it clear? So the amount of energy emitted from this body will reach this body, and the amount of energy emitted from this body will also reach this body. So they both are occurring at the same time, but the net effect is the actual heat transfer. Okay, so 10 watts are transferred from here to there, 5 watts are transferred.
This one, the screen. Fourth. That one from the last. Yes, this one.
This one?
No. That one from
Yes,
the last.
this one.
Oh, okay. Okay, so 10 watts transferred from this body to that body, 3 watt transfer from this body to this body. So the net transfer is 7 watt. Okay, so this is how we determine. So Fi to J, and similarly we can determine Fj to I. Okay, so as we discussed, the amount of energy is radiated from I, which reaches J, but at the same time there is amount of energy radiated by J, which reaches I. Okay, so in that case it will be F Ji equals to Q Ji divided by Aj Jj. Is clear? Now the amount of radiation emitted, it's a hemispherical problem, and there is double integration needed to actually determine the amount of radiation emitted from one surface to the other surface. Okay, we are not going to go into that integration, but anyways, whenever we have double integration, okay, there is possibility to switch the integral's position.
Yes, with the dA and dA.
Yeah. There is possibility to switch the integral positions. In the end, we will come out that this term becomes common. Okay, and when this term becomes common, that means we end up with a relationship which is known as reciprocity relation, and that reciprocity relation says that AI Fij is equals to Aj Fji. View factor for I with respect to j multiplied by the area of I is equals to view factor of j with respect to I multiplied by area of j. These terms are equal. Okay, this is a very important relationship which we will be using a lot. This is known as reciprocity relation.
And it depends on the area.
It depends upon, so the product of two things are same, area and the view factor of this with respect to the other. Similarly, area of that and view factor of that a surface with respect to this.
Both of them.
Yeah, so product of these terms will always be the same. Okay, so AI Fij is equals to Aj Fji. Okay, so in other words, I can write here A1 F12 is equals to A2 F21 if my surfaces are 1 and 2. Okay, or I can write A3 F34 is equals to A4 F43. Okay, when we write here the view factor, we don't read it as 34 or 12.
No.
It's 1, 2 from one surface to the other surface. we number the surfaces, and we read it like this. So you understand this reciprocity relation, okay? The derivation is not important here. I'm not going to ask you the derivation. You can go through it from the book if you want. But this relationship is very important, and we'll be using it in numericals a lot. Okay?
So you said the product, so if it's a vector, we have to use it as a vector?
No, I'm not talking about the vector product. It's considered as a regular multiplication. Okay? Is it clear? That's the reciprocity relation. Okay, now there are multiple ways of solving the view algebra or geometric factor algebra. So we have a geometric factor mathematics, which we have to deal here. Okay, so reciprocity relation is very important relation. Now there are some of the factors through which we can really determine by understanding, by inspection, that what will be the value of view factor. For example, if I have one ball and inside the ball I have another ball. So I have a ball, inside this ball I have another ball. Okay? So the amount of energy emitted from, by inspection, if I have a plane surface, okay? So the amount of energy emitted by the plane surface, if this surface is, say, I say 1. So what will be the view factor from 1 to 1? How much do you think will be the amount of energy emitted by one will reach 1? Nothing. Nothing. It will be 0. Right? If I have this surface like this, and the amount of energy emitted from here, let's say I call this as surface 2. So F22, what do you think? It's again 0. Any energy emitting by this surface will never reach the surface again. Okay? Let's say if I have this surface, but now the energy emitted from here. Okay, and let's say I call it 3. So F33. Will it be 0?
1. No.
It will not be 1, but it will not be 0. Why? Because we know that part of the energy emitted by the surface can reach the surface. But there is other part which is going outside as well. Okay? So it is not 0, it is not 1. It is in between. Is it clear? We are just telling it by inspection. So by inspection, if it is a plane surface, so F11 will be 0. By inspection, if it is a convex surface, then Fi to I from this surface to this surface will be 0. However, if it is a concave surface, then this is not 0. Okay? So this is what we told by just by inspection. Okay? Now, suppose you have this thing. I have one ball, inside this ball I have another ball. Okay, so the amount of radiations emitted by surface 1, let's say this is my surface 1, this is my surface 2. Amount of radiations emitted by surface 1 which reach surface 2. It would be, view factor will be F1 to 2 will be actually 1. All the radiations emitted from the surface 1 will have nowhere else except go to surface 2. Is it clear?
Yes.
This is what, how am I telling these numbers? Just by inspection. Okay, so it makes sense that any radiation which is emitted by 1 cannot go anywhere else except it reaches 2. So the total amount of radiation emitted by 1 will be reached by 2. Okay. In the similar case, the total amount of radiations emitted by 2, will it reach 1?
Not all.
Not all of it. Why? Because there is part of energy it can reach 1, and then there is part of energy which it can reach itself as well. Is it clear? So F11 is 0, F12 is 1, but F21 and F22 are not 0, neither 1.
In between.
It's in between. You understand the rationale behind?
Yes.
Okay. Amount of energy leaving 1 must reach 2. Amount of energy leaving 1 cannot reach 1 again. Amount of energy leaving 2, it's not necessary that all of it goes to 2. It can also go to itself. So amount of energy leaving 2 can reach to 2 again, right? And amount of energy leaving 2 can reach to 1 again. Okay, so both are possible. So F21 and F22 are not 0 or 1, it's in between. But F11 is 0, F12 is 1. We are doing it by inspection. Okay. Okay. Now there is symmetry. So suppose I have this square cone. I have this square cone. Okay. So the amount of energy leaving 1 will reach surface 2, 3, 4, 5. Okay. But by symmetry, I can see that the amount of energy leaving 1, which is reaching 2, and then which is reaching 3, and which is reaching 4, and which is reaching 5, all will be equal. Because all have similar surfaces, similar geometry. So the view factor from 1 to 2 or 1 to 3 or 1 to 4 or 1 to 5, it will be between 0 and 1, but they all will be same. Okay? And so since these are all symmetric sides, if it was not a perfect symmetry, then we cannot know what is the actual amount reaching from 1 to 2, or we cannot say that amount of energy leaving 1 reaching 2 or 3 and 4 and 5 are all same. Is it clear? So there are certain times we can just develop relations by symmetry. So this relation is developed by symmetry. Okay. Similarly, this relation. Okay. So amount of energy leaving 1 reaching 2, leaving 1 reaching 3. This will be same.
Because the axis.
Yeah, because there is symmetry, geometrical similarity. Okay. So F1 to 2 and F1 to 3 are same here. Similarly, F2 to 1 and F3 to 1 are also same. Amount of energy leaving 2 reaching 1, leaving 3 reaching 1. They both will be same by symmetry. Okay. Reciprocity relation is something you already now know. Then we have enclosure law or summation law. What does enclosure law or summation law means? The total amount of energy leaving one surface must have to reach other surfaces. And if you add them up all together, it will be equal to 1. So suppose I have 5 surfaces and I have F12, I have F11, I have F12, F13, F14, F15. So I have surface 1 which is emitting radiation which is reaching 5 surfaces including its own. Okay, 1, 2, 3, 4, 5. Okay, I don't know that what are the view factors from 1 to 1, 1 to 2, 1 to 3, 1 to 4, 1 to 5, but I know that the summation of all must be equal to 1. All the energy emitted by one must reach all the surrounding surfaces. And if you add them up all, it will be equal to 1. View factor will be equal to 1. This is the enclosure law, or you can say the summation rule. Now these are the 5 rules which you are going to be using to determine the view factors. Okay? And remember, if I want to know the heat transfer, I must know what is the view factor. If I don't know the view factor, I cannot determine the heat transfer, radiation heat transfer. Is it clear? So now you determine the relation. This is the relation for heat transfer. But I cannot determine the heat transfer if I do not know the view factor. And in order to determine the view factors, there are 5 basic ways. Reciprocity relation, okay, by inspection, by symmetry, summation rule, or enclosure rule, okay. And the 5th one is sometimes none of these rules are applicable, and then we have certain formulas developed for certain conditions, for certain situations. Then we might be using those formulas.
I hope the symmetrical one is the most question about it.
No. Okay, then there is also superposition rule, but it's kind of a symmetry rule. Okay, so amount of energy leaving 1 reaching 2, or amount of energy leaving 1 reaching 3 will be equal to amount of energy leaving 1 reaching 2 plus 3.
Yeah.
Makes sense? F1 to 2 plus F1 to 3 will be equal to F1 to 2, 3. So F1 to 2, 3 is equals to F1 to 2 plus F1 to 3. That's a superposition rule. But anyways, this is not really that important rule. Okay, so now we have this problem. We have to determine the view factors 1 to 2 and 2 to 1 for the following geometries. The best way is that whenever we are solving it, let's develop a matrix. Since we have 2 bodies, 1, 2, okay, so F11, F12, F21, F22. We need to determine F1 to 2, we need to determine this, and F2 to 1, right? So let's talk about the first body. One thing we can say, this is body 1. F1 to 1 is 0. In this case, this is 0. Okay. One thing we also know that F1 to 1 plus F1 to 2 must be equal to 1. Enclosure law. So this thing must be equals to 1.
So
F1 2 will be 1. So we determined the first thing. Let's talk about the other case. Okay. Now we know that F2 to 1 and F2 to 2, they are not 0, they are not equals to 1. Okay, but their summation is 1. Okay. However, now we can apply the reciprocity relation. Okay, what does the reciprocity relation say? Reciprocity relation say that A1 F12 is equals to A2 F21. Right? Now F12 is now known. Area 1 and area 2 are known. Okay? Surface area 1 and 2 are known. So we can find what is F21. So basically F12 will be what? 1. So that means F21 will be A1 by A2.
yes.
Is it clear? So we have determined all the view factors. Now let's come over to the other problem. I have a square, inside the square, or basically I have a cube, okay? The problem statement, it's not written there, but it's basically a cube. Inside a cube you have a sphere. You have a cube. Inside a cube you have a sphere, but the diameter of the sphere is d, and the cube has one side length L which is equals to D. So that means the sphere is actually very well fitted inside the cube, right? So now again I have two surfaces. One surface is of a sphere, other surface is of cube, okay? And I need to find out what are the view factors. So F1 to 1, F1 to 2, F2 to 1, F2 to 2. Okay, this is the case. Okay. Oh, sorry. In the previous case, we determined F2 to 1, but we did not determine F2 to 2. 1 minus F2 to 1. That will be F2 to 2. Anyways. Okay. So F1 to 1. Now let's talk about the second case. F1 to 1, F1 to 2, F2 to 1, F2 to 2. So one thing is very clear, that my 1 to 1 will be 0. This is a sphere and any image radiation emitted from it will be 0. So if this is 0, so 1 to 2 will be 1. So this is known now. Okay. Now let's talk about F2 to 1 and F2 to 2. Okay. For F2 to 1 and F2 to 2, what we can do is that we can develop the reciprocity relation, okay, to determine. So reciprocity relation is what? A1 F12 is equals to A2 F21, right? And F12 is known, which is 1. So basically F21 is equals to A1 upon A2. Now what is A1? A1 is basically the surface area of the sphere. So it's basically pi d square, right? Pi d square. And the surface area of the cube. A2 is the surface area of the cube.
Surface area of
D
the
squared.
for
6L square. Because it has 6 surfaces. So 6
for
L square.
the area of the circle bar over 4 d squared.
No, it's not the circle. I'm talking, this is a sphere. This is a sphere within a cube. Okay? So it's pi d square. But since L and D are same, so they will cancel. So it's pi by 6. So if we know F21, then we can find what is F22, because F21 plus F22 is equals to 1. Is it clear?
Yes.
So we determined for this case. Let's move towards the other case. Okay, partition within a square duct. Okay, so we have this square duct and one side length is L. Okay, so now I have this area A1, this area A2, this area A3. Okay, so I have this case. This is my duct. So this is A1, this is A2, this is A3, right? And what I need to know, okay, if I have 3, so let's first make the matrix F11, F12, F13, F21, F22, F23, F31, F32, F33, okay? And what I need to know is F12 and F21, right? This is what I need to find out, okay? Now, first of all these are plane surfaces. So any radiation emitted by them cannot reach them, right? So F11 is 0, F22 is 0, F33 is 0, right? Okay, this is a square duct. This is a square duct. That means this length is also L, this is also L. So by symmetry,
3 to 2
we know that F3 to 1 will be the same as F2 to 1. And F1 to 3 will be the same as 1 to 2. Because this is square duct. This is L, this is also L. Okay? So both have the same view factor by symmetry. Okay. So by symmetry, we know that f12 and f13 are same.
Each one will be 0.
So each one will be 0.5 because summation of them will be 1. It's clear? So now I know what is f12, I know what is f13. Okay. When you will be solving these problems, you will have to write these statements by symmetry, okay, by enclosure law, based on which law you are determining these view factors. You have to write it. Like for example, written here, by inspection, by symmetry, by enclosure law, by like this. Okay. This is enclosure law. Summation of all view factors is equals to 1. Okay. Now I have this. So from 1 to 2 and 2 to 1, I can use the reciprocity law. If I know the areas, then I can use the reciprocity law, which says that A1 F12 is equals to A2 F21. Now F12 I know. Okay. A1 and A2. A1 is what? A1 is, okay, let's talk about A2. A2 will be L. Okay. It's basically L multiplied by whatever the length, but anyways, the length are same for all. So consider just L. And what about A1? What will be the area here? So use the Pythagoras theorem. Okay, so it will be under root 2L. Okay, so now I know this, I know this, I know this, I can find what is F21. Is it clear? Others I don't need to know, because here it was just said that find F21 and F12. Right? So till here it is clear or not? Okay. Yeah, others we can also find out. Okay, if we know F12, F22 is 0, I can find what is F23.
3, 1, and 3, 2 will be 0, 1,
Exactly. Now this is a topic where I can play hugely. I can make a shape. I can make a shape where I can test all the laws from you. There are 6 laws, right? 5 or 6 laws. I can.
Give one example for that.
Yeah, don't worry. I will give you as many examples as you want. Okay, now let's say this is a fourth case, a case of coaxial parallel disk. Okay, so that means this is a case that you have a cylinder, small cylinder. The diameter of the cylinder is D and the length of the cylinder is L, but it is said that L is equals to D. Okay, so this is a small cylinder. And what are the surfaces we have? We have this top surface is A1, the bottom surface is A3, and the side surface is A2. Okay. Now what we need to find out is we need to find F12 and F21. Okay, F12 and F21. Now, first of all, let's make the matrix F11, 12, 13, F21, F22, 23, F31, 32, 33. Okay.
1 to 2, it's like 3D, like this.
Yeah, 3D.
Yes.
Sorry, 1 to 2?
Yes. The faces, how it is going through the A2.
From 1 to 2?
Yes, not above it. Okay,
I couldn't understand what you want to say.
Parameter.
Circumference. So, any radiation, let's say there is a big, let's say this room is not square, it is cylindrical. Okay, so that's the top surface. So any radiation from the top surface can reach the surface, while even moving in straight line can reach, because it moves in all direction, radiation. Is clear? So one thing is very clear, that this is a plane surface. So any radiation emitted by 1 cannot reach 1. So this is 0. Same for 3. Not same for 2. Because any radiation emitting by 2 can reach 2. So it's not like that for 2. Okay, this thing we know. And since the diameter here and diameter here are same, okay, so amount of radiation leaving 1 reaching 2 is the same as the amount of radiation, is the same as amount of radiation leaving 3 reaching 1. Okay. Yeah, reaching 2. So basically F 1 to 2 is equals to F 3 to 2. Right? But still it does not solve anything with us. We know that as per the enclosure law, this is equals to 1. Now here, there is no other way we can actually find out all the view factors. Now we have to move towards the tables. There are formula tables here, and these are as. Okay. If I have, this is as one surface and this is another surface, 2 parallel plates separated by distance L, then the view factor Fij is determined by this formula. Well, this is the width of surface I, this is the width of surface J. Okay? If I have 2 surfaces which are not parallel but they are making a specific angle, then the formula is this, Fi to j. We have to assume one surface as I, other surface as j, then Fi to j will be this formula. If I have 2 surfaces which are exactly perpendicular, like here, one surface wall, other floor, then the amount of energy emitted by one reaching the other, the view factor for it will be this. If I have 3 surfaces as an enclosure, 3-sided enclosure, then we have to introduce one surface as I, other as j, third as k. But Fi to j will be this formula. Okay. If I have 2 cylinders parallel, 2 parallel cylinders, then what is the view factor from one cylinder to the other cylinder? Okay. So one cylinder we will put it as I, other cylinder will say it as j. Okay, we know the radius of the 2 cylinders. Then the view factor will be this big formula. If I have one cylinder and one parallel rectangle, okay, so this is the cylinder, and then this is so we have a plate and a cylinder. Okay, so what's the view factor between a plate and the cylinder? So where plate is I and cylinder is j, so view factor is given by this formula. Given these distances known, L, S2, S1. Okay. If I have an infinite plane and row of cylinders, so let's say this is a shell and tube heat exchanger where this is your shell and these are the tubes. Okay. Then the radiation exchange from the shell to the tubes will be based upon this view factor. If I have now, these are the 3D, those were the 2D cases. Now this is a 3D case. If I have a cube, no, it's not a cube. If I have a parallelogram, you can say, okay. So with length L, Y, X, and I need to know how much is the radiation heat transfer from I to J. Okay, so then this big formula will be the view factor. Now our case is 2 disks separated apart. X bar is x by L. So x is this dimension divided by the distance between the two surfaces. Okay. Okay. So our case is basically this one, coaxial parallel disk. Okay. So I have two disks which are parallel, separated by a distance. So view factor from I to j, if I want to find out, I can use this formula. Fi to j is equals to half s minus s square minus 4 rj divided by ij. Since the two radiuses in our case are same, so rj and ij will be 1. Rj by ij will be 1. Okay, so now we have to first assume which is I, which is j. So suppose I want to know from 1 to 2. No, sorry, from 1 to 3. Suppose I want to know 1 to 3. If I know 1 to 3, I can find 1 to 2. Okay, suppose I want to know 1 to 3, how I can find 1 to 3? So Fij is F1 to 3. So my I is 1 and my j is 3. Right? So in this case, Rj will be radius of the third surface divided by Ri, radius of the first surface. Okay, but in our case, the two radiuses are same. Okay, but I need to find the s here. So s is basically 1 plus capital Rj square over capital Ri square. But what is capital Rj and what is capital Ri? Capital Ri is Ri by L. So radius divided by length. Okay, and here it is radius divided by length. Okay, so if I substitute the values here, in my case Rj and Ri are same. Okay, I don't know, was there any numerical value given in our case?
Yes.
Yeah, okay, because L is equals to D, so my Ri and Rj will be D by 2 by, so it's half. Okay, so that will give me the value of S. Based on the value of S, I'll find what is F31. Here, instead of finding F13, they find F31. It's okay, you can do like this. But then in this case, your I will be 3, your J will be 1.
3-1 equals 3-1-3.
3-1 equals to 1-3, yes,
Symmetry.
by symmetry. So here they determine what is F13. Now since 3-1 is equals to 1-3, so they determine what is F13. Now since F13 is known, so they will determine what is F12. Okay, and if you know what is F12, you can find what is F21 by the reciprocity relation. The same relation we have been using. A1 F12 is equals to A2 F21. Now F12 is known. Area 1 and area 2 are known. What is area 1? Area of the circle, which is pi by 4d square. What is area 2? It's the surface area of the cylinder, pi dl. But L is equals to d, pi d square. Okay. So if you substitute the values here, so you will exactly get that what is the F21 and what is F12. So similarly, you can find all the view factors. Is it clear?
Yes.
Right. Okay, so view factor topic is complete. Now we have understood the view factor completely. What is the time right now?
9 to 10.
We have a lot of time.
20 minutes.
Okay, so black body radiation exchange. So black body radiation exchange says that suppose I have two bodies and we assume that the two bodies are black bodies. So since we assume that the two bodies are black bodies, so the definition of a black body is that it absorbs everything. It does not reflect anything. Since all the radiation coming to it is absorbed, so nothing is reflected. Okay? So the radiosity will actually be equal to the emission. Radiosity is equals to what? Amount of energy emitted plus amount of energy reflected. But if it is a black body, then nothing is reflected, because all the incoming energy is absorbed. Definition of a black body: perfect emitter, perfect absorber, diffuse emitter. Okay. So if we know the emission of a black body is sigma T power 4. So just by knowing the temperature of the black body, we can know what is the emission. And then this emission will be the radiosity. Okay. So radiosity formula: Q is equals to FAJ, view factor multiplied by area multiplied by radiosity. But now for a black body case, this J is equals to E, because there is nothing reflected. The emission of the black body is the total radiosity, because J is equals to E plus rho G. But for a black body, rho is 0. Nothing is reflected. Any incoming radiation, it's absorbed. Okay. So J is equals to E, so we get this, and E is equals to sigma T power 4. So we can write here sigma T power 4. Okay. So this is for the case for Q I to J. If Q I to J, then F I to J, AI, and T power I. So let's talk about Q J to I. So F J to I, AJ, sigma Tj power 4, right? And the net exchange will be I to J minus J to I. Net exchange will be how much is the energy transferred from this to that minus that to this. Okay. So however, one thing, if you know, by the reciprocity relation, these two things are same. AIFIJ is equals to AJFJI, right? These two things are basically same. So the thing is that we end up with this formula. Qij is equals to AIFIJ sigma Ti power 4 minus Tj power 4, because delta Q will be Qij minus Qji. Delta Q is equals to Qij minus Qji. So if you do this minus this, where these two terms are same, okay, not cancelled, they can be taken as common because they are same. Okay, so AIFIJ sigma, these three things are common. So then it becomes Ti power 4 minus Tj power 4. Is it clear? So that will be my delta Q, and this becomes my formula for how much is the radiation heat exchange between two black bodies. If the bodies are not black, black body is an ideal body. If the bodies are not black, so there will be some emissivity. So you have to introduce epsilon here. If the body is not black, then there will be some emissivity. And so you will have a formula here with emissivity. And if you remember, now we are almost returning back to the formula which we had in chapter number 1. Okay, Q is equals to epsilon sigma area Ti power 4 minus T1 power 4 minus T2 power 4. There was no view factor at that time. Okay. Okay, so now we have the formulation here. Let's solve this problem. And this is the last problem. And with this problem, our chapter 13 is boom, over. Okay. This is kind of a difficult problem, so let's focus over it a little. Okay, we have a furnace cavity which is in the form of a cylinder, 50 millimeter diameter. Let me just first rub this. Okay, we have a furnace cavity which is in the form of a cylinder, 50 millimeter diameter and 150 millimeter length. So length is 150 millimeter, diameter is 50 millimeter. Okay, is open at one end. So one end is open to large surrounding that are at 27 degrees centigrade. So the surrounding is at 27 degrees centigrade. The bottom of the cavity is heated independently, as are three annular sections that comprise the sides of the cavity. All interior surfaces of the cavity may be approximated as black bodies and are maintained at 1650 degrees centigrade. So the thing is that this is a furnace cylinder. So this is the cylinder. Okay, outside is 27 degrees centigrade. Okay, outside is 27 degrees centigrade surrounding. Now bottom of the surface is heated separately, and then the overall body of the furnace, it's heated in three separate sections. So I have this section as section 1 section, then this is the other section, then this is the third section. Okay, anyways, for this problem we can assume that all the surfaces have the same temperature, although they are heated separately, but all of them have the same temperature. So that is 1650 degrees centigrade. So bottom has 1650 degrees centigrade, then this surface has 1650 degrees centigrade, this surface has 1650 degrees centigrade, this surface is 1650 degrees centigrade. It's okay? I can change the temperatures in the exam.
What will happen if it's
We will see. We'll see what will happen. Okay, what is the required electrical power input to the bottom surface of the cavity? What is the electric power to top, middle, and bottom sections of the cavity sides, back of the electrical radiator? Okay, we need to find the electrical power required to maintain 4 sections of the furnace at the prescribed temperature. The thing is that outside is 27 degrees centigrade. The furnace is 1650 degrees centigrade. It's open to atmosphere. Will there be heat loss from the furnace? Yes, there will be heat loss from the furnace. So if there is heat loss from the furnace, will the temperature of the furnace drop?
No.
Yes.
Yes, it will drop. But we need to keep the surface of the furnace same. So we have to electrically supply heat. How much heat needs to be supplied so the furnace temperature remains same? So in order to determine how much electrical energy needed to be supplied, we need to determine how much will be the heat loss. It will be according to that. If we supply that much energy which is actually being lost, then the temperature would remain same. Right? So that's the idea. Now we need to determine that how much is the heat loss from the furnace. Now this is the case. So we have the bottom, then we have one cylinder surface, then we have the bottom section, then we have the middle section, then we have the top section. And consider an imaginary top surface. Okay? So we number the surfaces as A1 as the bottom surface, A2 as the bottom section of the cylinder, A3 as the middle section of the cylinder. So this section is A3, A2, this surface is A1, okay, and this section is A4.
What if he divided? It is one same temperature, so does it matter?
But if we change the temperature, if I say that this is at 1650 degrees centigrade, this is at 1250 degrees centigrade, this is at 1450 degrees centigrade, this is 1800 degrees centigrade. Okay?
You already made the final?
No. Is it clear? Okay. So this is okay. So let's name this surface as A1, bottom surface, bottom cylinder A2, middle cylinder A3, top section of the cylinder A4, imaginary surface at the top. Let's consider A5. Okay, imaginary surface at the top, and we need two more imaginary surfaces. So let's say that between A2 and A3, an imaginary surface, we name it as A double dash, and between A3 and A4, another imaginary surface, we name it as A dash. Okay. Now we need to know that how much is the heat loss from the entire furnace. So that means how much is the heat loss from A4 to outside, A3 to outside, A2 to outside, A1 to outside. Okay, and outside means 5. So A4 to 5, A3 to 5, A2 to 5, A1 to 5. Okay. We'll explain that why do we need that. Okay, but in reality this is the case. We have the surfaces A1, A2, A3, A4, imaginary A5. So all the heat loss from A1 to 2 to 3, 1 to 5, 2 to 5, 3 to 5, 4 to 5. Summation of all will be the total heat loss from the furnace. That's the total energy.
A5 like the medium on the air?
Yeah, A5 is like the medium. So any energy loss to A5 will go to the outside. Because A5 is an imaginary surface, and then its outside is the medium air. Okay?
We can make it down. Okay.
What?
The A5.
No.
It has to be.
But because down is also of the surface of a furnace. It's a bottom surface. We need to know how much is the heat lost by the furnace. Assuming the furnace is fully insulated, any heat loss is not possible from the sides. Since it is open from the top, only heat loss possible is from the top.
Yes.
And we need to determine that how much will be that heat loss. Is it clear? So we need to determine what is the Q loss. But the Q loss will be equals to Q 1.5 plus Q 2.5 plus Q 3.5 plus Q 4.5, right? Or I can say Q summation of Q I5. Is okay? Summation of Q I5. Or I can say that what is summation of Q I5? Summation of Q I5 will be summation of, what's the formula for Q? Q is A I, okay, and AIF I5 sigma T I power 4 minus T 5 power 4. Is right? So you just substitute the value of I as 1, so that will be Q15.
Problem in F. The problem in F.
Yeah, problems are in F. Because these temperatures we know. The 5 temperature is basically the surrounding temperature. Right? That's the surrounding outside temperature. And it is known, 27 degrees centigrade. These section temperatures are known. Right? So we know that what are the temperatures of these sections. So we know what are Ti. Okay. Areas are also known. Okay. The only thing which is not known is this factor. If we know this factor, we will know what is the Q loss in total. Okay.
In Kelvin, the temperature.
Okay, now what I can do is that instead of writing it for Qi5, I can write it for Q5i. Because you know AIFI5 is equals to, so I can write this as summation A5 F5i. Reciprocity rule. Okay. Reciprocity rule is what? AIFIJ is equals to AJFJI. Right? That's the reciprocity rule. So I can use the reciprocity rule to convert this into this. The advantage of it is that now it's just one area that I will be using. Every time area will not be changing. It's a summation. So I have to use, previously I was using A1, then A2, then A3, then A4, then A5. Now it's just A5 I will use here. The factors will be, instead of I5, I will be use 5i. So now the factors I need to find is F51, F52, F53, F54. Is it clear? If I know these four factors, I will substitute it into this formula and I will find out all the total heat loss. Before proceeding forward, do you understand till this step or not? Is there anything that you do not understand? You can ask. So now this is a case where you can use, like we have in the previous case last time when we used for two coaxial cylinders, okay, for two coaxial circles. So A1 to 5 or 5 to 1. So it's like basically two circles, okay, two circular surfaces, okay, and they are coaxial. Coaxial means their axis is same. Okay, so we had that case previously, this one, when we used it. So 5 to 1 we can deal it like that simply by just using this formulation. I will find what is 5 to 1. Okay. So for that we need to know what is Ri, what is Rj. Okay, since we need to know 5, 1, so I will be 5, or you can say, you can determine 1, 5, then 1, 5 is equals to 5, 1. Both are okay. Okay. So substitute all the formulas and you will get what is F15. Okay, and you can find out what is F51, or you can directly find what is F51. Okay. Instead of doing F15, here it is done like that. First they find F15, then use the reciprocity to find F51. And by symmetry,
We already used reciprocity.
yeah, we already used reciprocity. It's okay. So directly this value is the same as this value. Okay. So we determine F51 from it. Is it clear?
Yes.
This step is clear. Okay. Now the next thing is that we need to determine what is F52, okay, and what is F53 and what is F54. Now the idea of determining F52 and F53 and F54 is the same. Okay, the idea of determining is same. So we will focus over F52, and then once you know how we determine F52, we will repeat the same procedure for F53 and F54. Okay. Now the thing is that the amount of energy, okay, F51, or you can say that F1 to 5, let me recall the relation here. Okay. So amount of energy leaving F51, okay, is equals to the amount of energy which is reached at 2 plus imaginary surface A double dash. What? Amount of energy leaving 1 is equals to the amount of energy reaching 2
Plus double dash.
plus A double dash.
Yes.
That's the enclosure law. Consider this as an enclosure. Consider this as an enclosure.
Okay.
The amount of energy leaving 1 is equals to the amount of energy reaching 2 plus A double dash.
2 plus A double dash equals 1.
Yeah.
Yeah. Better.
So F leaving 5 to A double dash is basically F5 to A double dash is equals to F5 to 2 plus F5 to 1. Okay, so you can also see this as from the other side. So this was if we consider this as an enclosure. However, if we consider the top side as an enclosure, okay, consider this top side as an enclosure. Okay.
A double dash equals A3 plus A dash.
So any amount of energy reaching A double dash is equals to the amount of energy which reached to A double dash will either can go to 2 or 2 to 1. From 5 energy will reach 4. From 5 energy will reach 3. From 5 energy will reach this imaginary surface A double dash. Right? So the amount of energy which reach from 5 to imaginary surface A double dash will be distributed between 2 and 1. Is it clear? From 5 energy will reach to 4. From 5 energy will reach to 3. From 5 energy will reach to A double dash. Let's say this is the imaginary surface A double dash here. So the amount of energy 5 which reaches to A double dash will be further distributed into 2 and 1.
Yes.
Okay? So 5 amount of energy that reaches from 5 to A double dash will be distributed between, which is going from 5 to 2 plus 5 to 1. Is it clear? Because for making you explain this enclosure, I have to, that's why I first gave you the example of the bottom enclosure. Okay. So that this is the enclosure law, you understand. So amount of energy reaching from 5 to A double dash is an imaginary surface. So this energy will further go where? To 2 and to 1. Okay?
Here.
So 5 A double dash is equals to F5 to 2 plus F5 to 1. First thing is that do you understand this relation or not?
Yes.
If you understand this relation, then I will move forward. If you don't understand this relation, I will stay here until you understand this or not. Do you understand this relation or not?
Yes.
Energy of 5 coming to A double dash will be equal to the energy of 5 coming to 1 plus coming to 2, because A double dash is an imaginary surface. Where will the energy go of A double dash? It will go to either 2 or 2 to 1. Okay? From 5 to A double dash is equals to 5 to 2 plus 5 to 1. Do you understand this relation or not?
It must be from bottom to up. Not
Yeah,
from
yeah.
up to.
Look, the thing is that if it is from bottom to up, we already applied the reciprocity. So we are not finding from I to 5, we are finding from 5 to I. And why did we apply this reciprocity?
Same
To
area.
make our life simple so that only one area is used. You understand? That's why I first explained it from the bottom enclosure. Now I'm moving towards the other way around.
So how it will be the same area?
Hmm?
How it will be the same area?
Look, previously it was AIFI5. So when I is 1, it is A1. When I is 2, it is A2. When I is 3, it is A3.
We make it from 5 to all the 5.
So now it's A5 only. It's okay? We did this just for our simplicity. Although the simplicity becomes a bit more hard for understanding sometimes. So Do you understand this relation or not? Important thing is that you explain to me that do you understand this relation or not. If you don't understand, I'll explain it again.
Brother, explain. I understand.
Okay? So if you know this, so we already determined what is 5 to 1.
Yes.
Right? We already determined what is 5 to 1. If we can determine what is 5 to a double dash, okay,
Use this relative.
then we can find what is 5 to 2. Is it clear?
Yes.
If we can determine what is 5 to a double dash, then we can determine what is 5 to 2. We already know what is a 5 to 1. So how can we find a to 5 a double dash? Now it is again the same problem but with a smaller cylinder. Previously it was this big length, now it is this length. Same problem again now. So repeating the same formulation again. Repeating the same formulation again, and we can find out what is 5a double dash.
Then
So it's like moving back to this formulation again. Previously we applied this formulation between 5 to 1. Now we are applying between 5 to a double dash. Is it clear or not?
yes.
Same formulation.
Yes.
So if you know what is 5 to a double dash, you already know what is a 5 to 1, you will know what is a 5 to 2. Is this step clear or not?
Yes.
Now in the same way, let's move towards the next step. So we know what is a 5 to 1, we know what is a 5 to 2. Now we need to know what is a 5 to 3. So if you want to know what is a 5 to 3, now we imagine this as our imaginary surface, a double dash. Okay? And now the equation will be f 5 to a dash, f 5 to a dash will be equals to f 5 to 3 plus f 5 to a double dash. f 5 to a dash is equals to f 5 to 3 plus 5 to a double dash. Do you see?
Yes.
We are repeating the same thing, but just on now much smaller scale. So now we know what is f5. We already know what is f5 to a double dash. We will apply the same formulation third time, but to find out what is f5 to a dash. Okay. So we'll find this. We will know what is f5 to 3. Is it clear?
Yes.
And now if you know what is f5 to 3, for f5 to 4, you don't need to apply this law again, because now you can use the enclosure law. f5 to 1 plus 5 to 2 plus 5 to 3 plus 5 to 4 plus 5 to 5 is equals to 1. f5 to 5 is 0, because f5 to 5 is a same plane, it's a straight plane. You know f5 to 1, you know f5 to 2, you know f5 to 3, only f5 to 4 is unknown. So you can determine it by the enclosure law. So I applied this formula 3 times. First time for the whole length, second time for this length, third time for this length. I told you from the beginning that this is a bit complicated problem, you understand?
5-page solution. 5-page solution.
Yeah, a little difficult. Anyways, do you understand the solution procedure or not?
Yes.
Yes.
Okay. Is there anything which you do not understand so far? You can ask. Because now you can see here that once we know all the view factors, now it is just the total Qi will be Q1 plus Q2 plus Q3 plus Q4. The total amount of heat loss will be the heat loss from 4 to 3, 2, 1. Okay? And in this case, the temperatures are of all these surfaces are same. If I change the temperatures, what will be the difference? Only these temperatures will change correspondingly. Okay?
The problem is if you add more area.
When I make a modification, I make an intelligent modification. I know what is the reasonable level of making modifications. Don't worry about that. The only thing that you should focus is when we are
Solving the problem.
when we are solving a problem, you should understand what we have, how we have done the solution. If you understand each and every step, then hopefully no big problem. Okay. So that's it. You add them up all together. So that is the amount of heat loss. Is it clear?
Yes. If I put the temperature outside more than inside.
That's a very good question. If you put the temperature outside more than inside, will there be any heat loss? And I asked you to find out the heat loss.
No, the heat will absorb inside the cylinder.
Heat loss from the environment.
Then there will be heat gain.
Yes.
Okay. So how would you deal with that?
You like it.
Anyways,
It's your turn right now. I'm not an example. What I have to do?
what you have to do is, then you have to find out all the view factors from 5 to 1, 5 to 2, 5 to 3, 5
This
to 4,
time
5
you
to 5.
start from 5. Or
Hmm?
you will just start from 5.
Yeah, that's it. Just switch it. So 5 to 1, 5 to 2, 5 to 3, 5 to 4, 5 to 5. And then just switch the temperatures. All the areas would be same.
Everything will be the same.
Everything will be same actually.
Then the Q will be negative.
Hmm? No, not negative.
Because it's lost.
Because then you will switch the temperatures. So it is surrounding minus 2.
The surrounding power 4 minus PS.
So with this, our chapter number 13 is finished.
Awesome.
Okay, and radiation heat transfer is done. So we are done with the conduction, convection, radiation. Now there is one lecture for the mass diffusion, and that's it. Your course of heat and mass transfer is done. And you would have studied to the level no people normally can, or your level of study has been exactly the same as the international standards. So you can go and give exam in MIT, Oxford,